Hey guys, I welcome you all to the 7th video of Module 5. And over here, this is the last video with respect to the theory part for linear regression, where I'm going to explain you about the optimizer called as gradient descent in order to minimize the cost function. So I'm going to discuss about the formula, again give you an intuition about that formula, that what each and everything means with respect to that given equation. Then what is this learning rate? What are the gradients in this equation? And how does it relate with this kind of a convergence that we had talked about in the previous video? So let's get into it. Alright guys, so we are in the final phase of linear regression, and this is my personal favorite part, as in how you go ahead and upgrade these values of W1, W2 and B, and you get the best values of the Y prediction from the linear regression. So far what we have done is that based on this data, we came up with this prediction equation, and then in the first attempt, that is the first iteration, you are going to come up with the random values of W1, W2 and B. And because these values are completely random, in your first attempt, you're going to get a very high cost function. And because your cost function is high, your model understands that you need to update the values of W1, W2 and B. And how does this updation works? So yes guys, that's where this optimization part comes in. And now there are a lot of different optimization algorithms. The one that I'm going to explain over here is the gradient descent algorithm. So how does this gradient descent algorithm works in order to update these values of the model parameters? So first of all, I'm going to talk about the formula, and let's just call that any type of your weight, any of your bias. If you want to update them, let's just call it by a single variable called as theta. And this theta can represent your any weight, any bias in your system. So how do we update this theta? So the process is that if you want to update this value of theta, you need what is the previous value of theta. Okay. If you know this previous value of theta, after this, you are going to subtract it with what? With the partial derivative of the cost function with respect to that theta. If your theta is W1, there will be equation for this W1 where theta will be getting replaced with that W1. Then if you are having W2 in your equation or in your prediction equation, you are going to have one more gradient descent equation for W2 and one for B. So if you are having 100 weights and one bias, you will have total of 101 equations like this, which will be updating the values of your respective model parameter. And this is how it works. But wait, there is something that we are missing, which we call as learning rate, which is the alpha over here. Don't really worry about all of these things. How did we get this kind of equation? Because that's something that I am going to explain you over here. Okay. And now to understand this equation, I need to give you some kind of a visualization of what's really going on. For this, you will require to know how does your cost function looks like. And currently, because we are dealing with the cost function called as mean squared error, because it's a square that we are having, you are going to get a quadratic basically. But yes, let me just write this cost function over here very quickly. It's 1 by n summation of all the rows of data of the squared error. This is your mean squared error. And because of this squared term, you are going to have that U-shaped curve. And if I draw it over here, and it's again very important for you guys to know that not all the cost functions are going to look like this. It's just that because we are having this mean squared error, it is looking like that. Okay. So let's say for example, it's going to look something like this. Okay. It's looking very weird. Let me just try to continue from this point. I guess no. Wait. This is better, right? Never mind. I'm not able to draw a proper curve, but I hope you will be able to draw it and it makes sense for you. So yeah, this is how the mean squared error will look like. And over here you are having this cost functions output, and over here you can have your respective model parameter. It could be W1, W2 or bias, right? So this will be your theta. This will be your output of that cost function. Now what's going to happen in your first iteration? Your theta value could be anything. Your W1, W2B could be literally anything. So for example, let's say that random value is somewhere over here, and I'll just call this as theta 0 or theta r for random. Okay. So this is your initial theta that you have handpicked. That's completely random. Now, because of this is random, we can clearly see that the cost is over here and is pretty much high. This is the least value of the cost, and this is what your model needs to achieve, the least possible cost. It will not always be zero, and in most of real cases, it will not be zero. You will be understanding this once we go into the coding part, and I'll be showing you why exactly I'm saying this. But for now, focus that this is the minimum value of the cost that we require, and this is present on this theta optimum. I'll just call it theta O for optimum. So what is the whole goal of this gradient descent algorithm? If your theta random is anywhere on your axis, anywhere, but for now let's say it's over here, the job of this gradient descent algorithm is to shift this theta r value to the optimal value of theta. Let's say, for example, if your theta r was somewhere over here, in that case, you need to make it move to the right side and get to that optimal value of theta. And how does it work? It works with this particular formula. Okay, don't really bother about how do we get this kind of partial derivatives, because I'll be explaining that once we'll be coding for that part, that for our particular use case, what will be this kind of equations that we'll be needing. But for now, just you can think of it as it's a gradient. Okay, gradient at a given value of theta, at a given theta. You can just think of it like that for now. All right. So at this point, what is the gradient? If I have to find it, I can surely go ahead, get this kind of partial derivative of this cost with that respect to, like, whatever kind of parameter you are dealing with. If it's W1, what is the gradient value with respect to that W1? Once you get that W1, what's going to happen? I am going to take that random value, that's my first value of this theta. I'm going to take that value. I'm going to do that subtraction part, and I'm going to remove some part of that gradient. Okay, and that sum part, what is that sum? Is actually the learning rate. I'll just color it with a different color altogether. Let me just call it as a orange color. This is what? It's your learning rate. Because I've already used orange, I'll choose maybe green. Green is fine, right? So this is your learning rate. It will tell you that how much amount of this gradient you want to remove from this theta in a hope that you get closer to that optimal value of theta. Typically we start with, like, the values like 0.001, and it's not the optimal value of alpha. It is actually the hyperparameter. You go ahead and try out with some different values of alpha and see which one is working the best. And to be honest, let's leave this learning rate for now as it is. I'll be coming on to this a little bit later, so that, like, once all the other aspects of this equations are clear, understanding this alpha value will be a piece of cake for us. All right. But for now, what we are focusing over here is that if we are on the right hand side of the optimal value of theta, how can we bring it to the left hand side? And if your theta was on the left hand side of your optimal value, how can I bring it to the right hand side? This is the first thing that you're going to focus on. Well, this kind of thing is getting governed by this negative value that you are having in your equation. It's because of this negative value, your model understands if your theta needs to go to the left or maybe it needs to go to the right. But at the same time, the sign of the gradient is also important. Okay. So if I have to explain this in a proper way, if we are to the right side of your optimal value of theta, in order to bring it to the left hand side, obviously from this value of theta, you want to remove some chunk. Now, what is that chunk? That chunk is nothing but your gradient value at that point. So if you will be removing something from this, obviously you will be coming to the left hand side. And let's say this is the next value of your theta. Now, just like this, if you are going to remove some more part from this, slowly you will see that you are going to get to that optimal value of theta. Now, let's say if you are on the left hand side of your optimal value of theta, then what's going to happen? Let's say if this is your random value of theta, for example. How is it going to go into the direction of your optimal value of theta? Again, this is where the gradient sign is important. Over here, the gradients are positive. Remember that this straight line will give you a positive gradient, and this type of straight line, which is the top part is facing to the left, is going to give you a negative gradient. Just remember this ideology. Now over here, this type of gradients everywhere if you see is always facing to the top right, and therefore this gradients will always remain positive, and therefore this is going in the left direction. But now what's going to happen if you're on the left hand side of the optimal value of theta? These gradients are pointing on the top in the left hand side, and therefore you can see that everywhere these arrows are pointing to the top left, and therefore these gradients are negative on the left hand side. And because they are negative, what's going to happen? This negative and this negative that is already present in your equation is going to convert this into positive. So now what's going to happen? Your current value of theta is going to get some portion of addition. And because it is getting addition, it's going to increase. And because it's increasing, it's going closer to the value of the optimal value of theta. So this is how this negative sign comes into the equation over here. If you are on the right hand side, it makes you go to the left. If you're on the left hand side of the theta optimal, it makes you go to the right. This is the process because of which we have the importance of the negative sign in this equation. Now, because this is happening with the help of gradients, we are trying to take away some of the gradients. You need to understand why actually gradients. Because you will notice the moment we are getting closer and closer to the optimal value of theta, the gradients value are decreasing. Initially, let's over here, there is some high value of this gradient. Okay, it's a steeper line over here, and therefore the gradient value is high in this case. Let's say the next value of theta you got is over here. At this point, this line is not that steep as compared to this line. So this gradient is less as compared to this. But now the moment you start going closer to that minimum point, you will realize that the gradients are going closer and closer to zero. And if these gradients are going closer to zero, or it becomes zero, what's going to happen? This term will be eliminated, or maybe very much small. And if this is small, there will be a very little updates that will be happening to this value of theta. What's going to happen if this value is, let's say, 0? It will be theta is equal to theta. Whatever was the previous value of theta is the new value of theta. And that's where the convergence happen. That is where that convergence of this theta value happens. The moment these values fall very close to 0, or maybe exactly 0, whatever it is. But yes, that's the importance of these gradients. It's because of these gradients, your theta will be updated in a certain way. If this value is high, there will be a lot of changes you will be seeing in the next value as compared to the previous value of theta. The moment this gradient values becomes less, there will be less updations you will be seeing in terms of, like, how much amount of change you saw over here will be pretty much less. And the moment this value becomes 0, there will be no updation at all, right? So yes guys, that's the process because of which we know that there is importance of gradients in this whole equation. So now we know that what is the reason of this negative sign and why do we require gradients. Now let's understand something more about this alpha. Let's say that if this was my random value of my theta in the first iteration, let's if I'm just going to multiply that gradient value at this point with a very high value over here. If it is high, what's going to happen? It can go over here, okay? It can directly go to this particular point. Because the value was high, we did a lot of subtraction from this value and it went to the left side. And on that left, whatever is the output, that's the output, that's the next value of cost that you will be getting over here. Now, after that next value, again, if that your alpha will be set once, okay, once it's set, you cannot change it. So because again, your alpha is high, it's going to give you more addition. And wherever is that addition, it's going to bump you over that particular point. So your this kind of idea of, like, going towards this optimal value of theta is not really achieved. But now at the same time, what happens if the alpha value is very small? If this is very small, let's say 0.000000001. So no matter, even if this value is high, it's going to convert it into a smaller value. And therefore, there will be a very minimal amount of changes that you will be seeing in your theta values. So maybe let's say the next value of the theta will be very close to it. Very less amount of updates you are going to see. It's going to take eternity to get to that convergence part. And then let's say if you're going to get that optimal combination of this alpha value, and you get this only after doing certain amount of tries, you typically start with like 0.01 or maybe 0.001, and then you maybe either decrease it by a factor of 10 or maybe increase it by a factor of 10 or whatever is the factor that you decide for your use case. So if you get that right combination, what's going to happen? Initially, if this gradient values are high, and if alpha is appropriate, it's going to give you a good jump in this particular direction. Now at this point, obviously, because the gradient has decreased, there will be a less updation or the less change of theta. So you will see that it's coming somewhere over here. Then the next time there will be a lot more, I should say a lot less change. And then similarly, you will see that it's the changes are very, very minute. And that's how you're going to get to that optimal value until your theta value stops getting updated or maybe gets converged at a particular point. So yes guys, this is how the gradient descent algorithm works. Wherever your theta value is, wherever your W1, W2B is, it will eventually get you to that minimal possible point. Alright guys, so before we wrap up the video over here, I just hope that like me, at least some of you have fell in love with this beautiful concept of gradient descent. And let's say if still any one of you are having any type of doubts, I am sure that this GIF is going to solve almost all of them. So on the left, what we are having is that cost function. On the x-axis, you are having some of the parameter. And because your parameter was initially completely off from the optimal value, you had a very high cost. And with respect to that, you will see that the line was over here. The prediction was somewhere in the bottom, very far away from the line of the best fit. But as the iterations went ahead, you can see that the cost is decreasing. And the moment the cost is decreasing, you can see that we are able to achieve that line of best fit after every iteration by iteration. And this is what happens with gradient descent. Your gradients are descending until it starts getting converged over here when the values of gradient starts approaching 0. And at that time, you see that the line of best fit has been achieved. So yes guys, that was about gradient descent. I hope you have enjoyed this particular video. I'll see you next when we'll be starting with the coding part now.